Okay, so for this video, we're going to look at heat. And I want to be clear that when we talk about heat, heat is not energy itself. Heat is the transfer of energy. So there's always energy going from one object to another object when we talk about heat. Right? So we're going to use the symbol Q to represent the heat transfer. That seems an odd symbol to use, but that's traditionally what we use. Um, and so we're going to talk about a couple of different things. We're going to increase or decrease the temperature of a substance. So we should have a delta T in our formula somewhere. The substance is going to have some mass. You can imagine that if you heat two objects to the same change in temperature and one of them's twice as big, you probably need to heat it up twice as much. So it has to depend on the mass. And it also depends on what the material is. One material might be completely different than another, and you have to have an idea of what to do with that. So this is getting into stuff I believe that is starting in chapter 20, if I can find it. Yeah, 20, section 20.2. So we're talking about specific heat. Right? The idea is that we have an object, we're going to heat it up. So let's make an object. Let's do a problem. Let's do, say, you're making a cup of coffee. So there's our water. It's 300 milliliters, and that means that it's 300 grams of water. Because the density is 1 gram per milliliter, or yeah, that's right. All right. So yeah, 1 kilogram per liter, and then there's 1,000 liters in a cubic meter. Yeah. Okay. So we have some water, and we're going to take it out of the tap, and we'll say that it is 5 degrees Celsius, and we're going to make coffee, which means we want it to get up to 95 degrees Celsius. We want to know how much heat it takes to do that. All right. Now, we are going to go later and talk about power, and our power is going to be our energy divided by the time, the heat that we need to put into the water divided by the time. So we're going to talk about making actual cups of coffee at some point. So we're looking at this. All right. We want to know how much heat we need. So Q here is going to be 0.3 kilograms. And then we'll have C here in a minute. And then we'll have 90 degrees Celsius as our change in temperature. And if we want to look up this, which is the specific heat capacity, then we're going to, essentially, this is another thing that is empirically found and it's in a big table, and you can determine what it is. We're looking for water. This is going to be 4186 joules per kilogram degrees Celsius. So the energy we would need is multiplying all this out. 90 times 4186 times 0.3. And so we need 113,000 joules. And note the degrees Celsius and the kilograms cancel out. The idea is that this specific heat capacity defines how much energy you need to change a specific amount of the fluid or of the material by a specific amount of temperature increase. All right, in this case, 1 kilogram, 1 degree Celsius. You would need 4,000 joules to heat that kilogram of water. And of course, it's different for every substance. You got this huge chart of the different things. So here is the bit is, how long would it take to heat this if we're using a stovetop kettle, or if we're using well, this is the thing, is that America doesn't use plug-in electric kettles all that much. For one reason, the electricity that we get isn't efficient at it. It can't, because it's 110 volts coming out of the wall instead of 230 in other countries. Countries that have high voltage tend to have more electric kettle uses. So let's say that you can put in, our power is 1500 watts. Well, the time it'll take is the total power divided by the rate. So the time, is the total energy divided by the power, and that is going to be this 113,000 divided by 1500, and that is 75 seconds. So if you've ever heated water in a microwave, and the microwave is 1500 watts, you need to leave it in there at least a minute and 15 seconds. If it's something like an 1100 watt, then you'll need to leave it in there something like something like 90 or 100 seconds. Right? So the gist of this is, what we have is we can relate it to real things. It takes longer to heat something up if you can only provide a certain amount of power. But what's going on is we're putting that energy into the motion of the particles in the water, which is changing the temperature. We're turning energy of one form. In a microwave, it's light. In an electric kettle, it's the energy that is stored in the current flow. So it's the potential energy of a battery or of a generator somewhere. And we turn that into the motion of particles in the water, and it heats up. All right, so let's go and get another page here. So we're going to do a plot here. You've probably seen this plot before if you've done chemistry. We're going to talk about the temperature of an object and the heat that's put in. And then we'll put in, so let's do some dotted lines here. All right, so we'll have, so this is going to be 100, let's do solid again. So let's erase that. So we're going to do 100 degrees Celsius, and we're going to talk about our block of ice or our cup of tea or something like that. So this is going to be 100 degrees Celsius and 0 degrees Celsius. Right? So here's our plot. We're going to start at some temperature down here. When we add more heat, we're going to change the temperature. All right, so we're doing this kind of differently. To get a certain amount of temperature change, we require a certain amount of heat. So we're taking a block of ice and we're melting it. And the ice has been in the deep freezer for a while. So this is the thing, is that at some point, the ice gets to the freezing point of water, and then it just sits there for a while. It keeps absorbing. I should change this. This is not what I wanted. So what we really want here is temperature on the y-axis and the heat that we put in on the x-axis. Got to be careful of that. All right. So we're heating up water. We add temperature. Sorry, we add heat. The temperature increases till, oops, it doesn't work. It flattens out again. Then it'll start, once we've melted all of the ice, then the water heats up again. Now work till we get to 100 degrees Celsius, and then it boils. So in these sloped parts, the heat we put in is MC delta T. But we need something to explain the melting and the boiling. So in these areas, these are the phase changes. And what we will describe is that the energy that we have to put in to cause a phase change is based solely on what the material is and the mass. This L here is what's called the latent heat. It is extra heat that's used or available that doesn't involve the temperature change, it involves the phase change. And there's a table for that. These tables, by the way, let's go back to the first one. Specific heat capacity is on page 557. Okay. And then the latent heat tables also exist, and they're on page 561. And note that this chart is also on that page. And we can identify certain regions here. All right, this is ice. This region is water. And then once the temperature goes back up, this is steam. And in these places where the phase changes occur, here and here, there is a mixture of ice and water or water and steam. So in these places where the phase changes occur, you pick what the phase change is and you look up the appropriate latent heat. So let's actually walk through a problem. This is going to be number 6 in the homework. We're just going to do it straight out. So this is, let's see, number 6. That is not what I wanted. Why are you doing that? All right. So we're going to change back to red. So number 6 in the problem is we have 42 grams of ice at minus 14 degrees Celsius. And we want to turn it into steam at 112 degrees Celsius. Okay. So there's 5 steps to this. One is ice heating. And then the second is melting. not melting. I'm melting, I'm melting. No, uh, melting. And then we have water heating. And then we'll have boiling. And then the fifth step is steam heating. All right. So each step is going to have something very separate. All right. We're going to have, for the ice heating, Q is MC delta T. Delta T is 14 degrees, and C is for ice. So you go look that up in your table of specific heats. And ice is about 2,090 joules per kilogram degrees Celsius. And then, of course, this 42 grams is 0.042 kilograms. So for the melting, Q is ML, and L is your latent heat of fusion, because these things work in reverse. You can go from water to ice or ice to water, and these things are all named in terms of going from water to ice or steam. So the latent heat of fusion is going to be this 3.33 times 10 to the 5 joules per kilogram. Then we have water heating. Q is MC delta T. We're going from the freezing point to the boiling point. Delta T is 100 degrees, and C is 4186 joules per kilogram degrees Celsius. Then we're going to boil. Boiling is a phase change, so we have Q is ML. And now we need the latent heat of vaporization. L vaporization, L of fusion. All right, so L of vaporization is 2.26 times 10 to the 6 joules per kilogram. And then the steam has to heat up. So Q is MC delta T. Delta T is 12 degrees, and C is for steam, which we have is 2010 joules per kilogram degrees Celsius. So that's 5 steps, and then you got to add all of those steps up. So you can do that. I trust you can do each of these steps and then add them up. All right, but that's the layout of number 6 that you have to, and you have to do that. All right, you have to consider what is the object, what is the material doing as you go through these things. So that's one thing you can do. You can just apply heat. But sometimes that heat comes from somewhere else. And you have to consider if you have so this is essentially number 5 in this homework, is you have a heat source, and so let's say you have a big bucket of water, and this bucket of water is at, I don't know, 25 degrees Celsius. We're looking at number 5 here, and we're going to put an object in it. And, we can make this a very hot object, say 600 degrees Celsius, and this is 20 degrees Celsius. And we're going to put them together, right? And so, this is 1 kilogram, and our water tank is 25 kilograms. Right. So, and of course, the phone is telling me that something's happened. All right. Yeah. So, Anyway, so the point of this is the object that we're putting in, it's a high temperature. In this case, it's a horseshoe in the problem. It has to go in and then lose its energy to the environment, to the water. So it's going to cool down. That energy goes somewhere, and the energy goes into the water, and so the water has to heat up. And so what we're going to have is the heat transfer for the object is equal to the inverse heat transfer for the water. All right, and that just means that we're going to take the energy out of the object and put it into the water. So we can figure out what that is. We'll have, say this is iron, and this is water. So we'll have MC delta T for iron equals MC delta T for water. And that's going to look like, so I'll write it down here, 1 kilogram times iron in the chart is 448 joules per kilogram degrees Celsius. And now here's the thing, we don't know what delta T is. These are different. These are different delta T's. And so what's going to happen is we're going to have the iron cool off. So we'll have T final minus 600 degrees Celsius. Well, that equals minus 25 kilograms times 4186 joules per kilogram degrees Celsius. And then the change for the water is going to be T final minus 20 degrees Celsius. And now you can solve for T final. All right, you're going to have some constant times T final on the left, some constant times T final on the right, and you solve for those. And you'll get that it'll heat up to something like 25 or 30 degrees Celsius as you take the energy out and you put it in the water. So you can't do this sort of problem, right? If you wanted to, you could think of, well, let's go and try to find Q of the object, which is this term. But you can't do that. You're missing the temperature that it ends up at. So that's the gist of these heat transfer problems, is sometimes you're just putting the energy in directly. Sometimes you're looking at energy coming from a source and you're coming to an equilibrium temperature. So the high temperature thing goes down and the low temperature thing comes up to some middle temperature. And sometimes your source of energy isn't heat. It's, number 7 is a kinetic energy turning into heat. And number 8 is, your source of energy is trying to cool a drink. So your drink is the energy source and you're melting ice with it. And you don't melt all of it. Or maybe you do, I don't know. So, these sorts of problems, you kind of have to sit and reason about them a little bit. And, what I'm trying to show in this video is how to do some of that reasoning. All right, so next video, conduction and radiation. Yippee.